In this video, we will meet some of the main functional groups we encounter regularly in organic chemistry. Functional groups are specific groupings of atoms within molecules that have their own characteristic properties, regardless of other atoms present in the molecule. Here are some functional groups we've met already. Alkanes. Alkanes are hydrocarbons containing no multiple bonds. We call alkane substituents alkyl groups, as in methyl, ethyl, and propyl groups. Alkanes are typically non-reactive and tend to provide the backbone of most organic molecules. We can abbreviate alkyl groups or other generic carbon substituents as R or R groups. Alkenes. Alkene substituents are called alkenyl groups. Some important terminology when working with alkenes is the vinylic versus allylic position. The vinylic position refers to the position of a hydrogen or substituent that is directly attached to an alkene's sp2 hybridized carbon atom. For example, in propylene, here are the vinylic hydrogens in red. The allylic position refers to the position of a hydrogen or substituent that is attached to a carbon atom adjacent to an alkene's sp2 hybridized carbon atom. For example, these are the allylic hydrogens in propylene in blue. This terminology will be important later. Alkynes. Alkyne substituents are called alkenyl groups. There are two types of alkynes, terminal and internal alkynes. Terminal alkynes have a CH, while internal alkynes have CC bonds at either end. Benzene rings. Benzene is a six-membered ring with three double bonds. Benzene substituents are called phenyl groups, abbreviated PH. Now let's take a look at some polar functional groups. Each of the following functional groups has a carbon connected to a more electronegative atom. This creates a dipole where carbon has a partial positive charge and the more electronegative atom has a partial negative charge. Alkyl halides have the functional group Rx, where R is an alkyl group and X is a halogen, FClBrI. Halogens are useful for functionalizing otherwise non-reactive alkanes. If the R group is an alkene, we call these groups alkenyl or vinyl halides. Alcohols. Alcohols have the chemical formula ROH, where a carbon is bonded to a hydroxyl group. Alcohols are weak acids and can also act as Lewis bases. We can usually identify alcohols by the suffix OL in their name, like in ethanol or isopropanol. Ethers. Ethers have the chemical formula ROR and are oxygen atoms flanked by two carbon groups. Ethers are also commonly used as solvents for reactions and can be made from alcohols using protecting groups, something we will work with later in the course. Epoxides are unusually reactive ethers and participate in several reactions that ethers generally do not. We will discuss epoxides in much more detail later in the course as well. Amines. Amines contain the functional group NH2, NHR, or NR2, where R is a hydrocarbon. The non-bonding electron pair on the nitrogen can act as a base. As a result, amines are very basic. We refer to amine substituents as amino groups. Let's move on to the carbonyl family. The C double bond O group is called a carbonyl group. The electron density in a carbonyl group is strongly polarized towards oxygen, and the electron-poor carbon bears a partial positive charge. Aldehyde. Aldehydes have the formula RCHO, where the carbonyl carbon is bonded to a hydrogen and an R group. An aldehyde bonded to two hydrogens is referred to as formaldehyde. Ketones. Ketones have the formula RCOR, where the carbonyl carbon is bonded to two carbon groups. The R groups can be the same or different carbon groups in ketones. Carboxylic acids. Carboxylic acid groups have the formula RCOOH, where the carbonyl group is bonded to a hydroxyl group and an R group. Despite the hydroxyl group, carboxylic acids are a distinct functional group from alcohols. Carboxylic acids, as their name implies, have an acidic proton. The pKa of acetic acid, a simple carboxylic acid, is about 4.76. Generally, the pKa values of carboxylic acids are close to this value and they do not undergo complete dissociation in water, unlike strong acids such as HCl. These final three functional groups are carboxylic acid derivatives. We won't talk about the detailed chemistry of these groups in this video series, but it is still good for you to be able to recognize them. Esters. Esters are similar to carboxylic acids, except the OH bond is replaced with an OR bond. They have the formula RCOOR. Amides. Amides contain a carbonyl carbon directly bonded to an amino group and have the chemical formula RCONH2, RCONHR, or RCONR2. Nitriles. Nitriles are CN groups with a carbon triple bonded to a nitrogen. As we've seen before, both the carbon and nitrogen in nitriles are sp hybridized. As always, let's do some practice. Identify and name the major functional groups in each of the molecules below. Feel free to pause the video and try these problems on your own first. Tyrosine is one of the 20 proteinogenic amino acids, the ones that make up the proteins in your body. As the name amino acid suggests, tyrosine has an amine and a carboxylic acid functional group. Furthermore, tyrosine has a phenyl ring with a hydroxyl group in its side chain. Guaifenesin is an expectorant that helps loosen congestion in your chest and throat, making it easier to cough out through your mouth. Starting from the left, the molecule has 2 ether functional groups and a phenyl ring. Toward the right, the molecule has 2 alcohol groups, which we refer to as a diol with di meaning 2. Acetaminophen is the active ingredient in Tylenol, which is used to relieve pain and reduce fever. This molecule contains an amide and a hydroxyl functional group and a phenyl ring. Pseudoephedrine is a decongestant commonly used to relieve nasal congestion caused by colds, allergies, and hay fever. It contains an amine and an alcohol functional group and also has a phenyl ring. As always, thank you for watching, and I'll see you next time.